Okay, so lesson 4.2, second lesson of differentiation, and hopefully a simpler concept and a shorter video. So to begin, if you haven't done so already, get onto Desmos. The class code's on the screen right now, and this is a much shorter activity than last time, but it's quite a collaborative one. So you will get the idea from the first problem. You have to, from the three graphs, choose f of x, f dash of x, and f double dash, the second derivative. And then once you've passed that, then you need to create your own equivalent problem for everyone else in the class. And then you will be able to see each other's problems and solve those as well. So that's your first step. And then once you've done that, we're going to get onto the main business for today. The main business is going to be exploring this idea of dx by dy. We're obviously really used to seeing dy by dx, but we're going to think about what dx by dy actually is. So, you can see three simple questions A, B and C on the board. I'd like you to have a go at these, pause the video and think about what I'm getting at with part C here. How can B help you with C or with A? How can dx by dy help you find dy by dx? Pause the video, have a go. Okay, so hopefully what you noticed there is that dy by dx and dx by dy are reciprocals, and this is another instance of the fraction notation helping us out. We know that 1 over 3 is the reciprocal of 3 over 1, and so it doesn't surprise us that dy by dx is the reciprocal of dx by dy. But let's have a little think about why that is and what dx by dy actually means, and for that we're going to turn to our notes. So here we are. We define dx by dy as being the reciprocal of dy by dx, assuming that dy by dx is not 0, because of course then the reciprocal would not be defined. And a second consideration for our definition is that x as a function of y is a one-to-one function, as in the inverse exists, it's a well-defined function, so we can move backwards and forwards between x and y. Now, what does this actually mean? Well, we know one way to think about dy by dx is that it's the rise over the run. Obviously they're thinking about a straight line, but the straight line could be the tangent to a curve at that point. But if that's true, then the reciprocal would be the run over the rise. And if we think about the restricting the rise to 1, what that means is dx by dy would be the run. So, in other words, for every 1 unit that y changes, that's the rise being 1, the x value changes by dx by dy. And you could imagine that for a given curve, if I just draw it here with the tangent. If I go up by 1, then I must go across by dx by dy. So that's what this expression means, and really, why are we interested in it? Well, it gives us a new way and a shortcut to find the gradient in some circumstances. So in the question that you've already thought about and looked at, let me just refocus. So that shortcut in action, if we've got x equals y cubed and we're trying to find dy by dx, let's quickly find dx by dy, differentiating in terms of y, give me 3y squared, so then dy by dx is 1 over dx by dy, so that's 1 over 3y squared. That answer in itself is fine, it's a closed form, it's simple, but of course We might be asked to do it in terms of x as well. So what we could do from the first equation is, from x equals y cubed, we could rearrange that to give y equals x to the power of a third. So dy by dx in this case is 1 over 3 times x to the power a third squared. So that's 1/3 x to the power minus 2 over 3 if we simplify it. So very quick, and we're able to express the answer both in terms of x and y. Now, we said at the top up there that the function had to be 1-to-1, but of course we could think about what we do when that's not the case, and a really common thing for us to do when we don't have a 1-to-1 function is to restrict the domain. So, the example underneath and on the next page tells us what we're looking at there. If we've got a gradient where we've got a quadratic of x in terms of y, we know quadratics like this are not going to be 1-to-1, and so we have to think about that part of the curve that we're looking at. So first thing I'm going to do here is I'm going to take this function, I'm going to sketch it, and I'd like you to pause the video and try that now. And then we're going to think about, okay, what about this point y equals 3? So have a go at sketching the function and finding the gradient. Okay, so you've tried to do your sketch. So by factorising here we can see x equals y times y minus 4, meaning that I have y-intercepts at 0 and 4, and I know I'm going to get a quadratic, so I need to just think about which way that's going to go. Is it going to be left to right, if you like, or right to left? What I would do there is I'd substitute or imagine what would happen if my value of y is positive and gets very big. Well, the right hand side here is going to also get very large and positive, and so I know that my function must come in from the right. It's a quadratic, so it's going to look something like this. This point being 4, this point being 1. Now, in this question, I'm asked about a point where y equals 3. And there's only going to be one solution here, because by symmetry, the midpoint must be 2. So there's going to be one solution that we're interested in, which means we can really just proceed as if this were a 1-to-1 function, because in the area we're interested in, it is. So we do exactly what we did before. We find dx by dy, which is going to be 2y minus 4. That means that dy by dx is 1 over 2y minus 4. And if y equals 3, there's no ambiguity, then dy by dx is 1 over 6 minus 4, which is a half. And that's the gradient at the point we're interested in. But flipping over, on the reverse side, we have the same function, x equals y squared minus 4y, but this time we're interested in x equals 5. I want you to pause the video, have a quick go at analysing this situation and try and determine why it's slightly different from the point we just looked at. Off you go. Okay, so if we take the same sketch that we had before, hopefully this is exactly what you did. We have it crossing at 2 points at 4 and 0, and we have the symmetry around 2. Well, here our condition is x equals 5, which is a vertical line, giving me 2 possible solutions. And that's something that we're going to have to analyse. We're expecting 2 answers. So, as we did before, dx by dy is 2y minus 4, which means dy by dx is 1 over 2y minus 4, but we need to find our y coordinates. So, we know x equals 5, meaning that I can take my original curve and I can represent that as a quadratic in one variable. substituting 5 for x, giving me something I can solve, and giving me the y coordinates of 5 and minus 1. So for y equals 5 or minus 1, those are going to be the 2 points we're looking at there. So therefore we're going to say the gradient is, in case 1, which is going to be the point up here, case 2 being the point down here. In case 1, the gradient is 1 over 2 times 5 minus 4, which is 5 is 10, so a sixth. But in case 2, the gradient is going to be 1 over minus 2 minus 4, which is minus a sixth. And what we notice about those, of course, is the second gradient is the negative equivalent of the first. And if we think about the symmetry of this graph, well, that's going to make sense to us, that the 2 points on those 2 branches are going to be have the same magnitude but opposite sign. Of course, that's a property of the fact that it's a quadratic, it's a parabola, and that would not always be the case, so we just have to take care in more complicated examples. Before we skip on, like I said, kind of a shorter video today, I just want you to look at how your CAS calculator can help you with questions like this, and in particular just to stress that we do have to break things down into a couple of steps on the Casio. So in order to answer a very similar question, the first thing that we would do here is solve the equation for y, giving me those equations of the 2 branches. And then once we've got those, we would differentiate with respect to x, showing that our calculator is really set up to differentiate with respect to x, giving me the 2 values when I specify exactly what value I am looking at. So that's about as much as we are going to cover today. I just want you to look quickly at the exercise. The contract questions are from 3 onwards, but I can't stress enough how important it is that you guys become really, really fluent at these basics with calculus. And if you want more practice and you have time, then do questions 1 and 2 as well. Aim to do them really quickly, aim to do them really accurately, and use it as a test for your fluency. But then the questions that I need to see from you by next lesson are questions 3 to 7, and looking through these, I don't think there is very much that will trip you up. Of course, let me know if I'm wrong about that, but 6 and 7 have you thinking a little bit more, but nothing that's beyond you. So best of luck and speak soon.